I'm gonna talk not just about the surface of the star, but more like the surroundings and what we are doing in, let's see here, in Uppsala in Sweden. So I'm part of a group called X-Wings. We are working on simulating the interior and the exterior of evolved stars. And my focus is on AGB stars and converting our models into some running our models in radiative transfer to create observables of these stars. And my talk is kind of my paper is not published yet, but is under revision and will be soon resubmitted after the first one. It's quite technical, and I understand there are quite many people that maybe are quite jet lagged, so I will not go into too many technicalities, but focus more on the results we have so far. And yes, so let's see here. We're running a number of codes in our group, primarily the first one is the primary one is Cobalt, which is a 3D radiation-hydrodynamical code that simulates both the interior and exterior AGB stars inside a box of varied sizes, as large as we can make them. The model I will showcase here uses a 30 by 30 by 30 astronomy unit box, and I'm using the code radiative-3D to simulate the our synthetic observables. And just because we have been using it a lot, I also mentioned here the Darwin code, which is a 1D code instead, where we can look at much larger scales, of course, than just a box of 30 astronomy units. So the aims in my project is, well, we have many questions, like how we predict lots of mass losses and dust-driven winds, and how observable are these processes, and detectable are they, resolvable in such things. And in the other direction also, can we constrain our model parameters through observations that where you, the observers here, come in? And how important is it to actually use a 3D model instead of 1D model? How important is it to not have spherical symmetry is a major question that I even write here. Quite important, I would say. So like I said, I wouldn't be too technical, so this is the I think the most technical slide. From Cobalt, the 3D models, we have I need to translate these data to be input data for my radiative transfer simulations. So and in radiative-3D you can't have aspherical stars. So I have to forego this somehow, and the trick I'm doing is that I translate the gas data from Cobalt into a specific dust species, where the instead of just having densities in each grid cell, I have the optical thickness in each grid cell, and I give it an opacity data of just being 1 in absorption, 0 in scattering. So a simplification of the star. The dust, on the other hand, that is forming in Cobalt is given in monomer densities that I can easily translate to mass density. Condensation fraction, which gives a grain size per cell, I reduce that to being 10 grain sizes, so 10 specific dust species in the cube, in the box. And for now, right here, I use the gas temperature from Cobalt as the dust temperature. I can explain why later if there's time. And then the dust opacity data is just from online, from laboratory data. And we assume forstrite and Mie dust in my radiative transfer simulation. So the data, the model I've been looking at looks something like this. It's an oxygen-rich AGB star, 1 solar mass, 2,800 Kelvin surface temperature average values in the simulations, and the pictures are slices through the middle of the grid into different directions. So here is the gas density, and the star is somewhere here in the middle. And the temperature, you can see the star here again, and the grain size of the dust. So the black here is where it's too hot for the dust to exist. And you can see there's plenty of dust around here, and also this cloud here, which you also see here in a different direction, where we have rapid grain size growth quite close to the star. It's also visible if I take a radial plot, and where the black line here is the average grain size in spherical shells. That would be your 1D model normally, right? The dark green patch is the standard deviation of each spherical shell, and the light green is the minimum and maximum grain size. You see the 3D effect here, as you have a great variety of grain sizes, and the rapid growth of grain sizes close to the star. These dust clouds, some of them don't survive. They just get destroyed quite quickly, and some of them do survive, like this one, and will then dissipate and move away from the star, starting the dust-driven wind that helps with the mass losses from the star. Let's see here. So I simulate images for one thing. So this is a 1 micron image of this model. You see the star here, and surface details of the star with the convection and everything going on the surface, variation in temperatures on the surface, and this black thing here is a dust cloud in front of the star, so really obscuring the star with the scattering at 1 micron. While at 10 micron, we instead get the silicate emission. So you can clearly see the star, both the dust cloud that is in front of the star and the star itself and dust around it. Mind, this is not a linear vertical scale in this image. I'm using a gamma curve to make both the star and the dust visible. Well, the neat trick here is that we can move the camera around and look in other directions. You can't really do that with the telescope. So this is in the opposite direction. So you have the dust cloud here going in behind the star, or in like from the side. So each model we have is, well, in fact, many models when it comes to observables, we can just rotate the camera, put it wherever we want, look at another time, and so there's lots and lots of data we can use for comparing with observations. So I do some tests with this data. So for example, I change the star from the nice, well, I think nice, not spherical symmetric cobalt star to a spherical symmetric star based on a Darwin model. And but I keep the dust from the previous model and compare what we can get. So for example, in the case of not resolving it, I imagine that we have a beam that is 30 by 30 astromega units. I mean, the beam in these SEDs here is the whole image, like these ones actually, the whole image here. And they are in 6 different directions, as indicated by the angles here. So see, there's a significant shifts in flux density on the same model, depending on which direction you are. So you can't really assume that what you see in the of one source, what the changes you can see on it is not really global. It can be something else going on the other side of the star that we don't know about. If I compare it with the spherical symmetric star, but with the cobalt dust there, we see the similar shifts in flux densities, depending on observed angle, some differences here. When I compare the SEDs of same direction, but with these two different models, I get similar size in differences between the same angle, observed angle, so to say. So the flux density shifts are both caused by dust around the star and the surface of the star, while the shifts in wavelength of the peak of the SED is mainly caused by the surface of the star. As in the spherical symmetric case, these shifts are much smaller. So here these shifts are only caused by dust around the star, while these shifts are caused by both the star and the dust. A major difference between using spherical symmetric star and not an asymmetric star. Well, I also try to create some kind of proof of concept observables. So in this case, I use VLTI as an inspiration. So I moved the model to 200 parsec. I convolve the images with a Gaussian beam that is corresponds to the angular resolution that the auxiliary telescopes of VLTI can get as a maximum. So it's not really what VLTI would see in this case, but more like what it would resolve. Again, we see the strong scattering from the dust obscuring the star and strong emission here. So here the main source is much smaller, suddenly is much larger at the longer wavelengths because of dust emission. So these kind of observations are already being done, as we probably hear a lot about this week, and some people here will probably talk about. But I want to showcase one example in the recent example from Leah Plankwart, I think that's how I pronounce it, who will talk later this week. So this dust here is more carbon-based. So it's AMC and SIC. And so a 10 micron, this 10 micron images would be more comparable, would be possibly to compare with my 10 micron image here due to the silicon. And they do say that these extensions are likely due to dust forming regions, which I can concur. My models say the same, that this is what we see in our models also. For example, if I compare the size of the main source, that would be the red contours here. See, it is much larger, more than around twice as large at 10 micron than at 1.6 microns. I also compare the flux densities in my images with what I find in the literature and see that, yes, they do correspond to, they do fall in the same ballpark as what is being observed of similar targets. So it seems my model is quite realistic. So as a final thing, I will do a short detour to my summary, and which is not really finished here, because I have some more things to show in the end here. But like I said, I've developed a method to create synthetic observables from our cobalt data. There are large shifts in the flux densities due to both surface feature and dust around the star, depending on which direction you're looking at. And there are differences between using a spherical symmetric star and not symmetric star. With this model, we do see very thick dust clouds being formed above the star. If they exist around other stars in reality, they should be possible to observe. It should be possible to detect and resolve. And what we are working on now is instead continuing this work on time-dependent data. So it goes in two directions, that we want to create tools for observers to be able, what is required for you to observe these kind of dust clouds. what kind of cadence do we need to observe them, and how often does these thick dust clouds form, and how often do you need to observe when the AGB start to find these. And I will show some kind of animation here that I made with the PDF by clicking it through. So this is the same model as before, but at another time. So I simulated time steps, images from time steps before and after what I've been showing you. So you can see here at this time step, you have these dust clouds forming around the star already here, and they are being blown away. And then you have this thick dust cloud forming above the star here and growing rapidly. I'm not simulating every time step here. I'm simulating every second snapshots that we have available. So there are more. There are data in between these steps also. And you can see how this dust cloud just kind of moves away. And same thing with the SEDs here. So the black curves are the current snapshot in 6 different directions, and the gray curves are all the other snapshots. Same data as before, and you can see how they move around quite a lot, and suddenly some of them falls down far down here. Is this realistic? I don't know. It's something we're looking into. So, which connects to the constrained simulation parameters. Is this realistic? What do we get in this model, or should we, with the observations, we should be able to constrain our model better? And for that, I want to mention Bernd Freytag's talk in this afternoon, where he's going to talk about more models that he's working on. And with that, I will say thank you and see if you have any questions.
Thanks, Joachim. Does anyone have any questions?
Hi, Joachim. Thanks for the nice talk. I was wondering a bit about using the gas temperature as the dust temperature. If you could elaborate a bit more about that.
So, okay, there's a long answer and a short answer. The short answer is that in the newer data, I'm using the gas temperature, but adapting it with a power law that is based on what that includes opacity effects due to Foster-Wright, so that I can include both the non-spherical asymmetric temperature we get from the star and non-gray effects from the dust. The problem with in radiation 3D is that I can only heat the dust with a spherical symmetric source. So that's why I have to include the star in a different way, and then I can't heat the dust, and then I have to use the temperature I have available for the model. So the dust is a bit too hot in these images I showed you, but not in these ones. Here I've already reduced the temperature with that power law. Yeah.
Does anyone else have a question? I will ask a quick one. Those dust clouds, I think, were mainly coming from convective cells on the surface of the star, right?
Sorry, say again.
The dust clouds that you're modeling, those are coming, sort of loosely speaking, from convective cells on the surface of the star. Do the models also include pulsations?
Yeah, I don't remember how long time span the whole time span for each model is, but if I did not include that plot here either, but if I plot luminosities of these SEDs over time, you get clear pulsations. And yes, Arif, who's supposed to come here, I hope he will manage. One of our PhD students has been looking much into the pulsations of these models. And I think Bernd will mention some of that also. So yes.
Any other questions?
So you mentioned several sort of different compositions. Is there a sort of typical dust composition in the models?
For oxygen-rich stars or in any star, do you mean?
No, just in the models you've been running.
Now, in this game, for these models, it's Fosterite mainly. It's not necessarily that, but that's as far as we know today. Fosterite for oxygen-rich stars would be most probable. And then the carbon-rich stars will, of course, have amorphous carbon or and SiC or other carbon-based, but that's complicated because it, let's see if I say it correctly now, it absorbs like crazy at short wavelengths. So it's very difficult to get anything out of the models because you don't see much.
Yeah, thank you.
Something like that.
Any other questions? We have time for one more quick question.
One question. You mentioned that from your models, you see that the dust forms close to the star, but how close? You're meaning just the stellar surface, the photosphere, or?
About, you hear me? About 1 stellar radii above the surface, so around, I don't remember the exact number now, 3 to 4 astronomical units from the center of the grid.
Okay.
So in the very beginning, that it's very much not very spherical.
Yeah.
Dust formation, because the temperature on the surface of the star varies so much with direction and time.
Yeah. Okay. Yeah. Super nice models.
Thank Bernd for that.